for many years now, my topic has been to study the sun. And when I was a student, I didn't even know that researching the sun was a job that would be possible. But when I was at university, then I started studying astrophysics, and that's when I realized that actually there's lots of interesting science questions to understand when it comes to studying the sun. So what I wanted to do is I've just got a few slides to give you an introduction to our sun, what kind of star it is,
science questions,
what's important
to understand
in terms of how do we study the sun, what wavelengths of light do we use, and what are the sort of physical principles that we have to think about. And so I think I might be able to share some slides with you. And what I want to do is have a look at the sun as we see it from various spacecraft. So my job completely revolves around using telescopes in space, and there's a reason for that. And that's because the sun gives off wavelengths of light across the electromagnetic spectrum. So from radio waves through optical, infrared, ultraviolet, X-rays, and even into the gamma rays. So what I like to do is sort of show this schematic of an electromagnetic spectrum and then look at how the sun comes across to us in different wavelengths of light. And we'll start with the most familiar, which is the visible light. So of course this is what you're used to. This is how we see the sun. If you can get a suitable filter and block out 99.9% of its light actually. And then when we take a picture of the sun using visible light, it looks like this. So kind of a featureless disk, except for these black spots that you see on the left-hand side. And that's what we call sunspots. And we've been looking at sunspots now for hundreds of years. In fact, perhaps even thousands of years if you take into account observers all around the world. And we know that the number of sunspots changes with time. Every 11 years, the number rises and falls, and that gives us something that we call the solar cycle. But for me, looking at the sun like this is kind of boring. What I would rather do is be able to go to shorter wavelengths of light, like ultraviolet light, and see the sun looking like this. So this is a picture taken at exactly the same time. The only difference is the wavelength of light that I use. And now you can see those sunspots are still there, but you see all this mottled structure across the surface of the sun. There are some bright patches and some darker patches, and you start to get a sense that there's a lot more to the sun than initially meets the eye in visible light. Then if I go to shorter wavelengths of light, more energetic, into X-rays, this is how the sun starts to look. And now it looks like a three-dimensional ball of gas. And what's really interesting, hopefully you'll see, is that in the atmosphere of the sun, we have these loop structures. So it is really three-dimensional, and the sun is full of loops of gas. And I'm going to come back to what they are in just a moment. So there you have three different wavelengths of light, and the sun looking very different when we use those three different wavelengths. So typically, as a space scientist, I would combine all this data together at the same time to get a full picture of what our sun is and what it's doing. And then, okay, I have one more picture here coming down into the X-rays, which the sun looks like this. But again, you're looking at the loops in the atmosphere of the sun. So there we have from visible all the way into X-rays. But then one thing we like to do is take advantage of the fact that the sun not only is a spherical ball of gas, but also has a magnetic field. And you'll be familiar with the Earth having a magnetic field, North Pole, South Pole. If I compare a picture of, let me bring these two up to make my point. So on the right-hand side here, I've got a picture of the Earth's, or schematic of the Earth's magnetic field. So it's as if you have a bar magnet inside the Earth, and then we would illustrate that by drawing field lines around the Earth. And I hope that probably you've seen pictures or images like this before. So that's on the right-hand side. But on the left-hand side, I've got a picture of the magnetic field of the sun. And what I hope you can see is that it's much more complicated than the Earth's. It's got magnetic loops all through the atmosphere. And rather than having an overall, what we would call bipole, which is basically one magnet with a north pole and a south pole, it's got lots of north and south poles. So you might be able to sort of find lots of loops in the atmosphere of the sun, and they're all emanating from different magnetic poles at the surface of the sun. And the thing that we've learned about this magnetic field, which ties us back to those sunspots that I mentioned a minute ago, is that the sunspots are sources of strong magnetic field at the surface of the sun, and magnetic fields emanate from them. But my sort of take-home message for you is when you think about the sun, don't just think about it as being a gas, but think about it as being a magnetized gas. And I've learned some really interesting things about this magnetized gas since I've been at university, working at a university. And this is a piece of physics I want to introduce you to. And you won't come across it unless you do physics at university, but I think it's really, really interesting. And it's a piece of physics that describes how an electrically charged gas, which is what the sun is made of, interacts with a magnetic field. So what I have is a little animation that shows lots of positively charged particles. So imagine they are protons. And the particles are hot, so they have a motion. When I set the movie running, you'll see it, and they're going to move around. And first of all, you'll see the particles moving freely. But then the animation introduces a magnetic field, and see how the motion of the particles changes. So let me run the movie. So you see the particles moving freely, they're hot. In comes my magnetic field and field lines, and now these particles are all influenced by the force of the magnetic field, and they spiral around it, a bit like going down a helter-skelter. They become helical in how they move. So here we go, the magnetic field comes in again, and things start to spiral around. Now, the reason I'm talking about this is because actually it's relevant to studying the sun, because this is how we think the gas, the electrically charged gas of the sun, interacts with the sun's magnetic field. And this interaction means that the gas is sculpted actually by the magnetic field, because these particles have to follow the field lines. So if I move on in my slides, I can show you this picture. Now this is a picture of the sun's atmosphere, of that very hot gas in the sun's atmosphere. And can you see how the gas follows these arch-like shapes? They are the arches in the magnetic field. And I've got a sort of schematic of a bar magnet there with a North Pole and a South Pole. But because the gas and the magnetic field are sort of interacting with each other, and in fact I sort of visualize them as being frozen together, the particles have to move along the magnetic field structures. And so they then reveal themselves to us. So this is a really, really important thing about the atmosphere of the sun. We have hot, glowing gas that traces out shapes in the magnetic field. And so when you next look at pictures of the sun, you'll be able to understand that everything you see, all the shapes in the X-ray images and in the extreme ultraviolet light images, all those shapes are sculpted by magnetic fields. And I think then I've got one slide to illustrate something that I haven't mentioned yet, which is the temperature of the sun. When we look at it in visible light, we're seeing a particular layer which has a temperature of 6,000 Kelvin. So that's the temperature scale that we use in physics. So you could, 0 Kelvin is minus 273 degrees Celsius. Doesn't really matter when you're up in thousands of Kelvin what the difference between the two scales is. So that's the visible surface of the sun. And then the gas that we're looking at that we see in X-rays, which is on the right-hand side, has a temperature of 2 million Kelvin. And that gas is so hot that the atoms have been ripped apart. So neutral atoms get ripped apart into the positively charged nuclei and the negatively charged electrons. And then those charged particles interact with the magnetic field and create those structures that you see on the right-hand side. So that were kind of some introductory slides to kick us off. I have got some more slides, so I could show them later. Maybe we could break, and if there's any questions now or any discussion points, we can take them.
Yeah, absolutely. So, so do you guys have any questions?
Well, I can.
Oh, sorry, I've unmuted you, Dr. Batson.
Okay. Right, any questions, guys? I'm just relaying from my sixth formers.
Otherwise, I'll go on and talk about some solar activity.
None yet. They're still thinking.
Yeah, fair enough.
Cool. Wellington, do you guys have any questions?
No, I don't think we do.
No? Okay, cool. I kind of have one, if you'll permit me. So this is kind of the opposite of of what I think of when I think of how temperatures of objects work, right? Like you expect it to be hottest in the middle, or I'd always thought the sun would be at its very hottest in the middle and then get cooler and cooler and cooler and cooler and cooler as it goes out.
Yeah.
And instead what we're saying is it's pretty hot in the middle, then it's like a medium temperature on it, like slightly further out, and it gets crazy hot even further out than that. I was wondering if you could explain how it works, or if you know.
Your intuition is right. When the energy source for our sun is in its very core in the center, where we have nuclear fusion, releasing energy from the material itself and turning that into heat. And then as you move away from the center, the temperature should drop, and it does. So it goes from 15 million degrees in the core to 6,000 degrees at the surface.
Mm-hmm.
And if you'd asked a scientist about what happens next in terms of what happens to the temperature as you go into the sun's atmosphere, if you'd asked that question in, say, the early 1800s, enough was known about physics by that point to say, oh, well, the temperature would keep dropping.
Mm-hmm.
But when we had the first instruments going into space above the Earth's atmosphere and with the ability to detect X-rays, they realised that wasn't the case. There'd been hints actually before then, but it was confirmed when we had the first space telescopes. And the reason that X-rays are important is that X-rays are given off by really hot gases. So the fact that you see X-rays tells us something about the temperature of the gas, and we can deduce that it is 2 million degrees. So it's completely counterintuitive. You're right, the temperature drops to the surface and then it hikes up again in the atmosphere. And the way we understand how that heating is happening actually comes down to the sun's magnetic field. And this is a really interesting area of physics that is sort of really important in solar physics, in that a magnetic field is able to store and release energy. It's a bit like a battery. You store it up and then you use it to do some work. And in the atmosphere of the sun, the magnetic field can store energy, release it, and it can go into heating the gas. And there's particular areas of physics to do with magnetic fields of how that happens. One is that you can power little explosions all over the atmosphere of the sun, and that those explosions get hot.
Sure.
Another, which is one of my favourite things, is that magnetic field lines have a tension, a bit like a guitar string. And if you imagine those schematics I drew of an arched magnetic field line, if I was to pluck the foot point of that field line, you could pass a wave up it. So it would go from the solar surface into the atmosphere. And that wave is a form of energy. And that energy might be able to heat the gas in the atmosphere of the sun. So we have these two different ideas, but the details are still being worked out. But it is completely counterintuitive. Shall I show you a consequence of this hot atmosphere? Because there is a really important consequence for us here on the Earth. And it's illustrated by this movie here. So what I've got in my slides on the screen is a picture of the sun at the center. So there's this very broad view. So this tiny, tiny orange spot is our sun. And what I've got here collectively are images taken from spacecraft looking at the sun and looking at all the space between the sun and the Earth. So this is the Earth over here on the left-hand side, and also over here on the right-hand side. So the reason I've got these two, this broad image, is because I'm using two different spacecraft to make this movie. It takes a bit of thinking about, so how to understand this. Well, what we did in 2006, and what NASA did, was launch two spacecraft into orbit around the sun. So just as the Earth is in orbit around the sun. But one spacecraft moved ahead of us in our orbit. And if you just sort of keep that picture in your mind, sun at the center of the solar system, Earth in orbit around it, spacecraft in orbit around it, but racing ahead of us. That spacecraft got to a point where it could then look back and see the sun and the Earth lined up. The second spacecraft went into orbit around the sun, but dragged behind us in our orbit. And after this, maybe draw a picture on the board to sort of think about this alignment. But what we did was we put two spacecraft in a position where they could both look back along the space from the sun to the Earth. And then we put those two viewpoints together here. But let me play this movie, because what you'll see is something really special, and I think quite profound actually, because you'll see how the atmosphere of the sun changes over time. What does this 1,000,000-degree magnetized atmosphere do? So I press play, and I hope what you can see is there is this constant outflow of material from the sun. The sun is always shedding its outer layers into the solar system. And that material creates a very, very, very extended atmosphere. And it washes over the Earth. It washes over all the planets in the solar system. And you can literally see it in this movie. And when I think about our relationship with the sun, I think about us as living in the atmosphere of the sun, because it's always expanding out into the solar system. So we are literally living inside the atmosphere of the sun. And as you can see, it's a gusty place with flows of material coming out. Sometimes the flows are fast moving, sometimes they're slow moving, but there's always an outflow. And the reason we always have an outflow from the sun is because it has a hot atmosphere. And in your physics lessons, you'll learn about hot gases have a thermal pressure. They can expand. And that's what the sun's atmosphere is doing. It's 2,000,000 degrees, it's hot, it's pushing out. And there comes a point where gravity is no longer able to hold on to this hot material which exerts a push. And so gravity can't constrain it anymore, and it just streams out into the solar system. And that's what we're seeing here. So this solar material, we call it the solar wind, was always flowing over us. And it was a big discovery in the space age in the 1950s and 60s, that the sun's atmosphere doesn't end where it might appear to have done in those pictures I showed you at the start. It actually ends 18 billion kilometers from the sun, which is way out beyond the orbit of Pluto. And we finally could detect the edge of the sun's atmosphere at that distance when the Voyager 1 spacecraft reached it in the summer of 2012. So imagine that the sun creates this huge bubble of magnetized gas because of this outflowing atmosphere. So there's the sun in the center, there's the Earth, and we're sitting in this expanding atmosphere. Now, there's also some other interesting activity that happens in the atmosphere of the sun. So, okay, here's just a reminder of the visible surface and the hot 1,000,000-degree atmosphere. Oh, I've got a couple of movies here actually to show the sun spinning over time. And in the movie on the right-hand side, which shows the 1,000,000-degree atmosphere, you can see the sun rotating, and it does that once every 27 days. But also what you can see are these flashes of light. So these are the explosions I talked about earlier happening in the magnetic fields of the sun's atmosphere. There's gorgeous loop structures, lots of changes, lots of energy release. It's really dynamic. And then I think I've got a movie to show you of, here we go, zoom into the sun. I want to show you my favorite event that the sun produced, and this was back in 2012. So I've got some pictures of the sun's atmosphere here, and I've zoomed in to a particular region, and it doesn't perhaps look like anything special, but if I run the movie, you'll see what happened on this particular day in June 2011 it was. First of all, I've got a bit of a processed movie that's made by Miloslav Drukmiller that just brings out some more of the detail in the structure of the sun's atmosphere. We're very into image processing to bring out faint features. So I play the movie, boom, you see this huge eruption of gas from the sun's atmosphere. And this is one of the most spectacular events that the sun has ever produced, but they are fairly common. So what you're looking at here is something called a coronal mass ejection. Not a very appealing name maybe, but does what it says on the tin. So corona is the sun's atmosphere, mass is what you're seeing moving up, and ejection is what you're seeing taking place. So here the sun is blasting into the solar system, the same amount of mass as you might have in Mount Everest, reaching a speed perhaps of a couple of thousand kilometers a second. Now, the material that you see here, a lot of it falls back down towards the sun. But what's not shown in this video is that a lot of the material makes it out into the solar system. And these kind of eruptions are really important because they show us what a dynamic and active star our sun is. But also when these explosions, when these eruptions of material move out into the solar system, they can reach the Earth, they can slam into our magnetic field, they can distort our magnetic field, and they can cause something that we call space weather, which affects our technology through satellites, communications, electricity distribution, and we can maybe talk about that a bit later on. And my job is all about understanding why and how these eruptions happen. And again, it comes back to the sun's magnetic field. And it turns out that actually what you're seeing here is the consequence of an erupting magnetic field, which carries the gas with it, because the gas and the magnetic field are frozen together. So we use the visible gas to tell us about how the invisible magnetic field is evolving. And then maybe this is something that you could do at school later on, but something I did quite early on was think about, well, why are these coronal mass ejections taking place? And I wondered if it was like throwing a ball into the air. So if it was something ballistic, that if the sun was able to throw this material up quickly enough, could it escape the sun's gravitational pull? And there's something that an object has that's called its escape velocity. And so here we have, this is the same eruption again, showing the material, but just from a different angle. And there's a way, I mean, I've got the equations on the screen, but you don't have to worry about it, but maybe you could do it with your teachers later on. There's a way to work out the escape velocity of the sun, knowing how massive it is, what the size is, and compare it to the kinetic energy of your erupting material. So I told you it's the same mass as a mountain. It moves at speeds of a couple of hundred, well, from a couple of hundred to a couple of thousand kilometers a second. You can rearrange these equations to work out the escape velocity. And then you can do a bit of physics to say, right, well, are these eruptions ballistic, or are they driven like a rocket leaving the sun? So maybe I'll just skip over that, and then you can work it out if you want to in your classroom. So coronal mass ejections have speeds of between, say, 200 kilometers a second and 2,000 kilometers a second. And if you work out the sun's escape velocity, how do those two sets of numbers compare?
Very cool. So I think what I love about this is that you're relating things that you can do in a classroom environment, like taking a bar magnet and measuring with like iron filings what's happening, and it's exactly those same processes that are driving these giant structures that dominate our solar system and dominate the whole universe. I think that's really cool.
Yeah, that's right. Everything I use begins with the physics I learned in the classroom. It's the physics of light, of electromagnetic radiation. It's electricity that generates a magnetic field. It's magnetism, it's forces, it's how things move. It's just you get into more and more detail as you go progressively through the system. But still, you know, the things I learned in school, I apply.
The things that, yeah.
Yeah.
Maybe this is a good chance to come back to the classes and see if you guys have any more questions. Where should we start? Can we pick a school?
Yeah, well, bottom one maybe.
Yeah, sure. Okay, cool. So.
Hello.
Hello. Do you got any questions?
Yeah, anyone got any questions? I know there was one earlier. They should be able to hear you, so. Okay.
What causes the coronal mass ejections?
Yeah, so that's exactly what I work on. What causes coronal mass ejection? And and having a more popular theory that it's to do with the shape and structure of the magnetic field in that region. So if you remember at the start, I showed pictures where we have arched field lines. And that's what you'd get when you have your bar magnet in the classroom and you look at the shapes of the iron filings. It's what we get in the Earth, it's what we get in the sun's atmosphere. But the sun is a really interesting object because it is a gas. And the gas moves. And I haven't really shown you any of that, but the whole ball of the sun is seething and there are fluid flows. And those fluid flows move the magnetic field because they're frozen together. And so I imagine magnetic field lines to be like elastic bands. They can be stretched and twisted and distorted. And when we look at these regions of coronal mass ejections, what we see is that the magnetic field has been distorted and twisted. So rather than forming a loop, it forms a twisted rope. So like getting a bundle of field lines and twisting them. And when you create that in the sun's atmosphere, it has a really interesting effect because the forces on those magnetic fields point up. And at some point, they can catastrophically erupt up. So, I mean, I'm looking around for some cables or something. I should have brought some props. So in my desk, I have lots of pipe cleaners, so I can twist up pipe cleaners and look and mimic the twisted field lines. So maybe just to sort of reinforce my point, if you had an arched field line with a curvature like that, the tension of that field line is pointing down towards the sun. So it's curved, and the tension, which is trying to straighten the field line, points down. When you have a twisted flux rope, which is also a bit distorted, the tension is up, the pressure is up. And so there's lots of work now where I try and observationally identify twisted field lines on the sun, and then my colleagues run models of twisted field lines to study how they erupt when you've got a computer simulation.
Cool. I think you've also highlighted there one of the things that I feel is a real misconception about science. It's not all about individuals. It's a hugely collaborative effort. So one person does one aspect, another does another, and then we will chat at a whiteboard and figure out what's going on, and then go back to it and try and adapt models, or try and adapt our observations, or try and adapt our analysis techniques to try and figure out why is nature doing all these crazy things.
Yeah, at the moment I work with people in my own group at UCL. I work with someone in Argentina, North America, Germany, Finland. I think they're my main collaborators at the moment. And so I do nothing by myself. It's all, well, I mean, I work day to day by myself, but then we collaborate, we get together, we meet, we write papers together, and everybody brings in that different expertise.
Cool, great question though. Yeah, any more questions? So we'll come back to Dr. Batson. You guys have any more questions?
Got some feedback. Any other questions here? No? I think. Can you?
How close have we ever got to the sun from the satellite?
How close have we ever got to the sun?
Oh, okay. I think I heard the question as how close have we ever got to the sun? Give me a thumbs up if that was right. Yes, great. So in the 1980s, we had a German/American mission called Helios, and that got to around somewhere between 1/4 and 1/3 of the distance between the sun and the Earth. So pretty close. That's around the orbit of Mercury, so the closest planet to the sun. And yeah, that's as close as we've been. Well, there was only the 2 spacecraft that did that. We typically don't send things close to the sun because it's very challenging, because the heat increases, the particles coming out of the sun, the density increases. But you may have heard in the news recently that there are 2 missions being planned to be launched very soon that will go back to the sun. One is the NASA, well, it used to be called Solar Probe Plus, and now it's called the Parker Solar Probe. And that will get just ridiculously close to the sun. That will come within 6 million kilometers of the surface of the sun. And okay, that might not sound very much, 6 million kilometers, but if you remember, there's 150 million kilometers between the sun and the Earth. That is really skimming the surface of the sun. And that's going to be in such a challenging environment. They've had to build a very significant heat shield to protect the instruments on board. It's going to take 7 years to get into the right orbit where it gets that close. It's a very challenging mission. So that's in America. Meanwhile, in Europe, we're building a mission called Solar Orbiter, and that will be launched about the same time as the Parker Solar Probe. We don't go quite as close. We go to around the orbit of Mercury. But we will have cameras on board our spacecraft, so we can look at the sun from that close proximity and measure the solar wind and the coronal mass ejections as they blast over the spacecraft. So they will launch 2018 and 2019. So in the news in the coming years, when you're studying science, you'll be able to see the first results coming from these spacecraft. And in fact, maybe I could just share my screen again quickly, because this slide I have here shows a model of the Solar Orbiter mission. So this is a model of the Solar Orbiter spacecraft when it's at closest approach to the sun. So you can see some solar panels coming out the right-hand side. There's various booms with instrumentation on it, but on the left, that white sheet that you see, that's the thermal shield of the spacecraft. So the sun is off to the left, and there's a temperature gauge, and you can see that the front side of the spacecraft, the sun-facing side, will heat up to 500 degrees Celsius. So what's that, twice as hot as your oven maybe? And
pretty warm.
Pretty warm. Meanwhile, our instruments want to operate at room temperature, so 22 degrees Celsius. So we have to stop all that heat from entering our spacecraft and keep our instruments operating. So that gives you a flavour of the environment that Solar Orbiter will be in when it gets close to the sun. And this spacecraft is being built in Britain right now, in Stevenage at Airbus, and various university groups are building the instruments on board. So the engineers here at MSSL are building various bits of instrumentation that will fly on this. So it's kind of been really exciting, because I can walk down to our engineering workshops and I can see what's going to end up in space in 2 years' time.
I love that about working here. Like just wandering over and seeing something that's going to Mars or something that's going right next to the sun or something. It's very cool. Cool. Does that answer your question in Trafford? Yeah. Awesome. You guys have a any other?
No, I think any more? No, I think we're okay.
Cool. Okay. I'll just switch over to Liverpool. Oh, and also, I'm conscious of working on the YouTube live stream, so if any of the students on the live stream have questions, feel free to put them into the chat window and I'll pass them into Lucie. So, Liverpool?
Can you hear me okay?
Just about. You might need to shout a bit.
Okay. If you can't hear me, I'll type it. Basically, I was just wondering about if the photons coming from the sun, if CMEs or the magnetic field have any effect on the photons that come from the sun.
Great question.
Yeah, it's a good question, and it's good to think about what's leaving the sun. And in fact, so I've forgotten already the order of the question, but basically is, do the photons and the magnetic field or other things interact with each other? And they do. So there's an interaction between the photons leaving the sun and the sun's magnetic field itself. And that's because ultimately there's an interaction between the magnetic field and the gas which is emitting those photons, so the hot gas that's emitting it. And what we see is that the photons are polarized. And that is really, really useful, because in fact we can then detect those polarized photons and work backwards in order to tell us something about the magnetic field that polarized them in the first place. So we use this to make maps of the sun's magnetic field. And without that piece of physics, we would not be able to understand the sun as a magnetic star. We would have no knowledge that the sun was magnetic. Okay, we could still perhaps see these images of the loops and make an inference, but the polarization of the light allows us to directly measure the field and build up a three-dimensional picture of what that's like. It's probably one of the most important observations, I would say.
Cool. Does that help with the question?
Yeah. Brilliant.
Yeah, good question.
Okay, I'm conscious we need to wrap up in about 5 minutes, so I'll just head back to Dr. Dotson's class because I think I might have cut you guys off earlier. So, do you guys have any other questions?
I had one actually.
Yeah.
How do you test that an object that's going to go that close to the sun, so a a probe or whatever, how do you test it with the conditions that it's going to experience that close to the sun in the lab, in the clean room or whatever?
Yeah, because we have to test. You're absolutely right. You can't take the risk of spending perhaps billions of euros on a mission that then won't work because it will melt in the intense heat of the sun. And in fact, if I screen share again, luckily enough, I have some images to show what happens. So I hope can you see this one, which is an image of the heat shield being tested in, I think this is in the Netherlands. So this is the European Space Agency mission Solar Orbiter. And this is that heat shield that will have to withstand temperatures of about 500 degrees Celsius facing the sun. You can see it's got some holes in it to allow our telescopes to peek through. But what's happening here is this heat shield is being lowered into a tank. Off to the left is the white lid of the tank, so that the heat shield will go in, the lid will come on, and the tank will be evacuated to recreate the vacuum of space. And then there are many, many high-intensity lamps which will be focused on this heat shield to simulate the intense radiation of the sun and make sure that the heat shield can withstand it and do its job. And this is just one of many tests that happens, but it's a key one for when we go close to the sun. But also the spacecraft and the instruments on board will be shaken to test that they can withstand the launch itself. So when the rocket engines go off and there's lots of sound generated, which is a vibration, that could potentially break instruments. So we vibrate them before launch just to make sure that's okay. They'll be subjected to extreme thermal testing. All the electronics will be tested. There is a very rigorous series of tests of the instrumentation by themselves, and then once everything's been put on board the spacecraft itself. But this picture I really like, because I just think it shows really nicely that you need really large scale facilities to test something the size of a spacecraft.
Amazing. So, so I think we have to wrap up in 3 minutes. So are there any last questions? Maybe put up your hand if you've got a question, and I'll... No? Okay. So I have one final one, and I'm springing this on you a bit. I'm sorry. So what, based on all the amazing things that you've done in your career, what pieces of advice would you give to school pupils thinking about getting into either science or engineering or maths?
I would say, because you have to work, well, to be successful in anything, you have to work hard. And so you have to pick something you really enjoy. And in science, you have to have a really inquisitive mind to be really focused on quite narrow questions. So for me to want to know, well, how does a magnetic field evolve to produce a coronal mass ejection? It's a pretty narrow question. I'm probably a little bit obsessed by that because I'm so interested in it, and that's why I'm happy to spend many hours every day thinking about it. You know, I go home, I still think about it. I'm driving into work and I think, oh yeah, I've just suddenly made a connection and worked through a problem. So I never really switch off from it. I think finding the thing that you're passionate about is key, because then you'll work hard, and when you work hard, you're successful. And so that means getting a broad range of experiences so that you can identify that thing that really motivates you. So getting work experience, making use of links that you have, attending summer schools, doing things like this, listening to online chats, so that you can identify what it is that really makes you want to get out of bed in the morning. That would be my advice.
Awesome. I think that's great. So I think I'm afraid we've got to wrap up for today. I'm sure if you guys have any burning questions, no pun intended, I came up with that one on the spot, then you're welcome to drop me an email or get your teachers to drop me an email, and I'll pass them on to Lucie. And yeah, and otherwise, hopefully, so we have another webinar next week with Dr. Martin Archer about how to build a lightsaber. So if you've ever wondered how to build a lightsaber, maybe join us next week at the same time. Otherwise, I hope you've all enjoyed this, and yeah, thanks again, Lucie.
Yeah, thank you. Nice to see you all.
Cheers. All right. Bye.
Thanks for joining us today. Please like, comment and subscribe. Let us know if there are any space science topics you'd like to see in the future. You are learning through space with Spacelink. See you soon.